All right. So here is what we will be looking at in the context of chapter 8. So Oppenheim and Schafer, chapter 8. The contents of the chapter you can see are given in slide number 1. So, but let us look at what we are going to be covering. Okay, in 8.1 we're going to be talking about the discrete Fourier series for a periodic signal. Discrete Fourier series. Okay, we will use the acronym DFS. In some books, you will also see the acronym discrete time Fourier series. Both are the same. Basically, it's a Fourier series representation of a periodic discrete time signal. Okay, 8.2. 8.2 is whenever we study a transform, we always study its properties. The properties of the discrete Fourier series. Okay. Then we take the first step towards getting the transition that we are interested in. So we then say, okay, typically a Fourier transform is for absolutely summable signals, right? Discrete time Fourier transform. On the other hand, if you have a periodic signal, you may be able to get a Fourier transform representation if you allow Dirac delta functions. So this is the part where we will introduce that. This is the part where we say we will look at the Fourier transform of periodic signals. Okay, so we are going to introduce the notion that periodic signals can have a Fourier transform. Of course, they can have a Fourier series represented. That's what we have covered in 8.1 and 8.2. But we see that they can also have a, okay. Then we look at the Fourier transform and sample it. Sampling the Fourier transform. Okay, what do we mean by that? A Fourier transform is evaluated at omega all around the omega axis. Okay, this is the omega axis. So basically, you start from omega equal to 0 and go all the way to omega equal to 2 pi. Okay. Now, instead of evaluating it at all frequencies, let us say that you evaluated it at 0, pi by 4, pi by 2, 3 pi by 4, pi, and again 135 degrees, 180 plus 45, 225, 270 and 315 and then 360 basically. So, in this particular case, you have 8 samples of the discrete time Fourier transform. So basically we are saying, okay, I can sample it at or compute the discrete time Fourier transform at periodic intervals. Okay, that is what is called sampling the Fourier transform. Okay, this then helps us move into the discrete Fourier transform. This is the foundation by which we will then get the representation of the called the discrete Fourier transform. Okay, DFT. That's the focus of what we are going to be studying in this chapter, and this comes from the understanding that periodic signals can have a discrete Fourier series representation. You can also get a Fourier transform representation. Given a Fourier transform, you can sample the Fourier transform and recognize that this will also is helping us get to the point where we now define the discrete Fourier transform. Basically, if you want to give a definition for this, the discrete Fourier transform is the Fourier representation of finite duration sequences. Representation of finite duration sequences. Okay, so basically we have a finite length transform for a finite length sequence. So that is what a DFT is. Then of course, as always, we will study the properties of the DFT. of the DFT. And one of the most interesting and useful applications of the DFT is going to be the property of convolution. Okay, property of convolution, application of DFT. This is convolution. Okay, now using DFT, we obtain a form of convolution called periodic convolution. We obtain periodic convolution. Okay. However, in LTI systems, what you have is not periodic convolution, but we have linear convolution. Okay. So basically, there is a difference between the convolution that happens when you use the DFT to obtain the computation compared to what we want. So the last chapter that we're going to be looking at is how can we use the DFT, because it's a very efficient computation, but not get circular convolution or periodic convolution, but get linear convolution. Okay, very important. So computing linear convolution. This is what we want for in all LTI input-output systems. Our interest is to get linear convolution. Okay, but we want to compute that using the DFT, because we will show that what we get is a very efficient algorithm that we are going to do. So this is the layout of chapter 8. We start with DFS, then move to DFT, and then finally look at an important application. Okay, please read along as we are progressing, because this chapter has got a fair amount of theory and a lot of explanations, which are excellent explanations are given in the book, and therefore very helpful if you are able to follow along. All right, here is where we begin today's session, where we start to look at the discrete Fourier series. Discrete Fourier series. Remember, the discrete Fourier series is intended for periodic signals. So we start with a definition of what type of signals, and then look at the periodic representation. Okay, so here is the framework. So we consider a discrete time periodic sequence. Discrete time periodic sequence, we're going to denote it as x tilde of n. The tilde is going to always denote some periodic function, and square brackets means it is discrete, not a continuous function, with period equal to n. Okay, with period n. Now, what does this mean? The statement that it's periodic says that x tilde of n will be equal to x tilde of n shifted by any multiple of the uppercase or the period. Okay, Rn. So for any integers r comma n. Okay, so for example, if n is equal to 10, x of 1 is the same as x of 11, is the same of x of 21, x of 31, all of that. So basically that's what it means. So that's the notion of periodicity. So for any integers r comma n. Okay, and whenever you have a periodic signal, so this is the framework, this is a periodic signal, and if you have a periodic signal, we can then apply the concept of Fourier series, and the Fourier series tells us that you can represent the periodic function or the periodic signal as a sum of weighted harmonically related sinusoids. Okay, so the periodic signal x tilde of n can be represented, okay, that's the basic Fourier theory, can be represented by a sum of harmonically related complex exponentials, by a sum of harmonically related, basically the harmonics of the fundamental harmonically related complex exponentials. Okay, so what do we mean by that? If you define a complex exponential, okay, so a complex exponential, it will be of the form e power j omega n. That's basically the form of a complex exponential. Now we want those complex exponentials that are periodic with period equal to n, right, in the time domain. Periodic with period equal to n. So we find that the complex exponentials that satisfy this can be written as with period n are e subscript k n, which is given by e power j 2 pi by n k n. Okay, so the fundamental frequency is equal to 2 pi divided by n. The harmonics are given by 2 pi by n times k. K can be 0, 1 all the way to n minus 1. Notice that k becomes equal to n, you get back the frequencies start to repeat. So basically once you go beyond that. So the number of distinct exponential sinusoids is equal to number of distinct sinusoids equal to n. Number of distinct sinusoids equal to n. Okay. So given that, our expression for the periodic signal can be given as x tilde of n will be a sum of these sinusoids, weighted sinusoids, k equal to 0 through n minus 1. The sinusoids are e power j 2 pi by n k times n. Notice that that's the sinusoids, there are n of them. They are going to be weighted by certain coefficients. We are going to call them as x of k. Each of these k n sinusoids is going to be weighted. So this is the coefficients. We call it x tilde of k. And then we also introduce a scale factor of 1 over n. We will explain what the scale factor is there for. So basically the expression that we have is, we have a periodic signal x tilde of n, it's got period equal to n. There are n complex exponentials which have the same period equal to n, and we are writing it as a sum of weighted as a weighted sum of these complex n complex exponentials. Now, there are certain important properties that we would like to understand and highlight so that it becomes easier for you to see and to appreciate what is happening in the, maybe a note that will be very helpful for you is that when you are talking about continuous time, in continuous time, periodic signals have got a Fourier series representation. The Fourier series representation involves an infinite number of harmonics, right? Fourier series representation involves an infinite number of harmonically related complex exponentials. Okay, because the summation will be from minus infinity to infinity. Harmonically related complex exponentials. That's the Fourier series representation for continuous time. Okay. Now, on the other hand, the discrete time has only n distinct sinusoids. So, therefore, there is a big difference. In discrete time, the Fourier series representation involves only a finite number of complex exponentials. Finite number of complex exponentials. Okay, and the finite number is equal to the period. And this finite number equal to the period. Okay, if the period is n, you have only n complex exponentials that we have to worry about. Okay, And this particular notation that we have introduced, e power j 2 pi by n, 2 pi by n into k, that's your times n will be a complex exponential. The short form is e subscript k times n. Okay, this is the kth harmonic. Okay, k stands for kth harmonic. Okay, so let us look at it a little bit more carefully. Okay, so we have this notation e subscript n, which stands for e power j 2 pi by n k n. I hope you're not, you will no confusion here. And k can be 0, 1 all the way through n minus 1. So there are n distinct complex exponentials. Okay, now there are two types of notations that you will come across. The first notation, okay, I'm going to give you that, it will be helpful for you. So whenever you read the book, you will be helpful. The first notation is a notation which is W, uppercase W subscript n. Okay, this is e power minus j 2 pi by n. Okay, so now given that this is the W notation, we can then say that ek of n, okay, can you just help me with this? This will be Wn minus kn. Okay, Wn minus k because to get rid of the minus sign, and then k because the kth harmonic, and then kn. Okay, so e power j 2 pi by kn, this can be written in this form. Okay, and there's one more notation which will be used and is helpful for you to keep that also in mind. That is a notation of basis functions. So they say that, okay, we have at the end of the day, these complex exponentials are nothing but basis functions, and so the notation of the basis functions is given as psi of k comma n. Psi of k comma n is the same as e power j 2 pi by n times kn. Okay, so the complex exponential can be written in terms of the psi, it can be written in terms of the w, or it can be written in terms of the original e expression. Okay, this is the same as e kn. Okay, so there are three notations where you can see that these will be used, and it will be helpful for us to keep track of this notation. Okay, property number one. Property number one. The first one we see is that these complex exponentials have a periodic nature. E of k plus ln. So if you shift k by a multiple of n, what does that sinusoid become? Okay, e power j 2 pi by n. Instead of k, we have k plus ln times n. Okay, so this is nothing but e power j 2 pi by n kn times the second term e power j 2 pi by n ln n. Okay, cancel off the n, so it's a multiple of 2 pi, so this term is equal to 1, so therefore this is equal to e power j 2 pi by n kn. Okay, so we can now write down the first property. The first property has basically these sinusoids are periodic. E power k subscript k plus ln times n is identically equal to e subscript k of n. So this is the reason why we don't need an infinite number of harmonics, we just need a finite number. There are only finite number of these functions. Okay, the second aspect is a very important property. It is a property of orthogonality between these sinusoid basis functions. Okay, property number 2. Property number 2 says that if you look at the following computation, 1 over n summation n equal to 0 through n minus 1 psi of k comma n. So this is one of the basis functions, and if you take its multiplication or correlation with another basis function psi conjugate L comma n, n is a time index, the first basis function is k, the second basis function is the sinusoid with the nth harmonic. This will be equal to 1 if L is equal to k, only if L is equal to k, and is equal to 0 if L is not equal to k. This is called the property of orthogonality. These basis functions are orthogonal to each other, and therefore they give us some very unique properties which we will be able to leverage and be able to develop. Okay, now if you want to, maybe it's a good idea for you to verify. Let me just show you what are the steps to verify and then ask you to complete the verification. Okay, so verification of the principle or the property of orthogonality. So this left hand side can be written as 1 over n summation n is equal to 0 through n minus 1. Now substitute for psi kn and psi conjugate ln. So this will be e power j 2 pi by n k n. The second term will be e power minus j because of the conjugate 2 pi by n ln. Okay, so this can be written as 1 over n summation n equal to 0 through n minus 1 e power j 2 pi by n k minus l times n. Okay, now please go ahead and complete this expression and verify that this, so basically the intermediate steps are there, and the final step will be that what you will get is this is equal to, this summation is equal to 1 if k minus r, that's k minus l, k minus l is equal to any multiple of n. It will be equal to 0 otherwise. Okay, that's the final answer that you will get. But the important thing to note is that what is the range of k? K is 0 through n minus 1. L is equal to 0 through n minus 1. So therefore, k minus L cannot be any arbitrary multiple of n. The only value that is possible and only multiple of n that you can get is equal to 0. Okay, k minus L equal to 0 or k equal to L. Okay, so basically the principle of orthogonality has been verified, that these basis functions, if you correlate with themselves, if you correlate with itself, you will get 1. If you correlate with any other basis function, the value will be 0.